In this video, just wanted to take a look at two of our theorems from section 7.4. The first one being theorem 7.5, the triangle proportionality theorem, and just looking at an application. Notice in this triangle, we have a segment that intersects two sides of the triangle and is parallel to the third. According to the triangle proportionality theorem, that should divide these two sides into segments of proportional lengths. So if I'm trying to find x, I can compare x to the 8 centimeter length in the same way that I can compare 1 5/10 centimeters to this length. Now, I might have to do a little work there because I'm only given this total distance. So if I take 7 centimeters and subtract 1.5 centimeters, 7 minus 1 is 6. 6 minus 5/10 would be 5 5/10 centimeters for that distance. And so that would be the value I would put into that position. Now, notice I could have also compared the x to the 1.5 as 8 to the 5.5. There are a lot of different proportions that have the same value as this one, because the important thing is that the cross products are equal. Now, in this case, do I really need to do cross products? No. If I multiply both sides by 8 centimeters, that would leave x alone. So 1.5 times 8. I'm going to do that on my calculator here. So if I take 1.5 times 8, okay, I get 12. Okay, I kind of knew that. 1 times 8 plus half of 8. So centimeters times centimeters would be square centimeters. So then when I do the division, 12 divided by 5 5/10, we get this 2.18 repeating. And that's actually appropriate for this because I am in centimeters, the metric system. We use decimals rather than the fractional values. So we'd have 2.18 repeating. Notice square centimeters divided by centimeters would just be centimeters. So there's an application of the triangle proportionality theorem. Now, we also had the converse of that theorem. And so our question here is segment BD parallel to segment AE? So the triangle proportionality theorem says if they're parallel, the two sides that are intersected by the parallel segment divides that into proportional lengths. The converse says if the lengths are proportional, then this segment is parallel to this segment. So what I'm going to do is set up a proportion, or excuse me, a ratio of these. So 2.1 meters to 6.3 meters and 1.4 meters to 4.2 meters. Notice I could have also set up my ratios here to here as long as they were corresponding. So, on my calculator again, I'm going to take 2.1 divided by 6.3. I don't know if that's showing up on the screen there very well. Notice I get 0.3 repeating for that. My labels of meters would reduce. So this is 0.3 repeating. If I do the same thing for the other ratio, 1 4/10 divided by 4 2/10, I also get 0.3 repeating. because those ratios are the same, that segment BD has divided these two sides into proportional lengths. So by the converse of the triangle proportionality theorem, we know that segment BD is parallel to segment AE. There are applications to the triangle proportionality theorem as well as its converse.